Liquid metal embrittlement or LME damage mechanisms as a part of environment-assisted cracking. Description of liquid metal embrittlement damage mechanisms based on API 571. Liquid metal embrittlement or LME is a form of cracking that results when certain molten metals come in contact with specific alloys. Cracking can be very sudden and brittle in nature. Here's a comprehensive and detailed description of liquid metal embrittlement or LME damage. Introduction. Liquid metal embrittlement is a type of environmentally assisted cracking that occurs when certain ductile metals or alloys become brittle and fracture rapidly due to the presence of specific liquid metals. Unlike traditional corrosion, which involves material degradation over time, LME involves a sudden loss of ductility and strength, leading to brittle failure. Fundamental mechanisms of liquid metal embrittlement or LME. Number 1 is conditions for LME, susceptible material, usually ductile metals such as steels, aluminum alloys, copper alloys, nickel alloys, or titanium. Liquid metal environment, a specific liquid metal that interacts with the susceptible metal, such as mercury, zinc, cadmium, bismuth, lead, or tin. Contact and penetration. The liquid metal must come into direct contact with the solid metal, often in a liquid state under operating conditions, stress or strain. The material experiences tensile or shear stresses, which can be residual, from fabrication, or operational, such as thermal expansion, pressure. Number 2 is embrittlement process, wetting and penetration. The liquid metal wets the susceptible metal's surface and infiltrates along grain boundaries or existing flaws. Grain boundary weakening. The liquid metal segregates preferentially at grain boundaries, reducing cohesive strength. Brittle fracture. Under stress, the weakened boundaries facilitate rapid crack initiation and intergranular fracture, often with minimal plastic deformation. Key characteristics of liquid metal embrittlement damage. Brittle fracture in ductile metals. Despite the ductile nature, the presence of liquid metal induces brittle failure. Intergranular fracture mode. Cracks propagate along grain boundaries. Sudden failure. Damage progresses rapidly once initiated, often without significant prior deformation. Minimal plastic deformation. Fracture occurs with little warning and minimal necking or ductility. Common materials and liquid metals involved in liquid metal embrittlement are the following. Susceptible materials. Number 1 is steels and or stainless steels with common liquid metals are mercury, zinc and cadmium. Its typical environments are chemical plants, thermometers, dental amalgams. Susceptible materials. Number 2 is aluminum alloys with common liquid metals are mercury and zinc. Its typical environments are manufacturing, aerospace. Susceptible materials. Number 3 is copper alloys with common liquid metals are mercury and zinc. Its typical environments are electronics, plumbing. Susceptible materials. Number 4 is nickel alloys with common liquid metals are mercury and lead. Its typical environments are nuclear reactors, chemical processing. Susceptible materials. Number 5 is titanium alloys with common liquid metals are mercury and bismuth. Its typical environments are marine, aerospace. Factors influencing liquid metal embrittlement includes, number 1 is material microstructure, grain size, purity, and heat treatment influence susceptibility. Number 2 is liquid metal composition, purity and wetting characteristics affect infiltration. Number 3 is stress state, higher tensile stresses promote crack initiation. Number 4 is temperature. Elevated temperatures can enhance wetting but may also influence diffusion rates. Number 5 is exposure duration, longer contact increases risk of infiltration and damage. Liquid metal embrittlement mechanistic details includes, number A, wettability. The liquid metal must wet the solid metal surface, which depends on surface energy and temperature. Good wettability facilitates infiltration along grain boundaries. Number B, segregation and penetration. The liquid metal penetrates microstructural features, especially grain boundaries, cracks, or inclusions. Segregation weakens the cohesive strength of boundaries, lowering fracture resistance. Liquid metal embrittlement mechanistic details. Number C, crack initiation and propagation. Initiation often occurs at microstructural flaws, inclusions, or residual stresses. Once initiated, cracks propagate rapidly along grain boundaries, leading to brittle fracture. Manifestations and damage features of liquid metal embrittlement includes intergranular fracture surface, characteristic appearance with brittle, granular features along grain boundaries, crack nucleation sites, microstructural flaws, inclusions, or areas of residual stress. Sudden failure, no significant prior warning, failure occurs rapidly once critical penetration occurs. Detection and identification method for liquid metal embrittlement includes but not limited to: number 1 is fractographic analysis. Examination of fracture surfaces reveals intergranular brittle features characteristic of LME. Number 2 is microscopy. SEM, scanning electron microscopy, can identify grain boundary infiltration and microstructural features. Number 3 is chemical analysis. Energy dispersive X-ray spectroscopy, EDS, can detect liquid metal residues at crack sites. Number 4 is non-destructive testing. NDT ultrasonic testing, radiography, or dye penetrant may detect subsurface or surface flaws. Prevention and control measures for liquid metal embrittlement includes but not limited to: number 1 is material selection. Use materials resistant to LME, such as avoiding susceptible alloys and selecting compatible metals. Number 2 is environmental control. Minimize contact with liquid metals, employ barriers or coatings. Number 3 is design modifications. Reduce residual stresses, avoid sharp corners, and implement stress relief. Number 4 is operational controls. Limit exposure time and temperature in environments containing liquid metals. Number 5 is inspection and monitoring. Regular inspections, especially after exposure, to detect early crack formation. Liquid metal embrittlement or LME is a damaging phenomenon where certain ductile metals become brittle and fracture rapidly when they come into contact with specific liquid metals under stress. It involves infiltration of liquid metal along grain boundaries, weakening the microstructure, and leading to intergranular brittle failure with minimal plastic deformation. Understanding the specific susceptible materials, liquid metals involved, environmental factors, and microstructural conditions is essential for preventing and managing LME damage. Liquid metal embrittlement affected materials based on API 571. Many commonly used materials including carbon steel, low alloy steels, high-strength steels, 300 series SS, nickel base alloys and the copper alloys, aluminum alloys and titanium alloys. Here's a detailed explanation of materials affected by liquid metal embrittlement or LME. Introduction. Liquid metal embrittlement, LME, is a phenomenon where certain ductile metals or alloys become brittle and fracture suddenly upon exposure to specific liquid metals under stress. Not all materials are susceptible. The likelihood of LME depends heavily on the material's microstructure, composition, and environmental interactions. Primary materials affected by liquid metal embrittlement or LME includes: number 1 is steels, including carbon steels and stainless steels. Steel susceptibility includes many steels, especially high-strength, low-ductility variants, are vulnerable. Austenitic stainless steels, like 304, 316, can be susceptible under certain conditions. The mechanism of liquid metal embrittlement to steel materials includes: liquid zinc, mercury, or cadmium can infiltrate along grain boundaries, causing intergranular brittle failure. High residual stresses or tensile stresses exacerbate susceptibility. Primary materials. Number 2 is aluminum alloys. Its susceptibility includes aluminum alloys, particularly those with high purity or certain microstructures, can be affected. Mercury is a common liquid metal involved. The mechanism of liquid metal embrittlement to aluminum alloys includes: mercury wets aluminum surfaces, infiltrates grain boundaries, leading to embrittlement. Primary materials. Number 3 is copper and copper alloys. Its susceptibility includes copper, brass, and bronze alloys are vulnerable to mercury-induced embrittlement. Application of copper and copper alloys mostly on plumbing, electrical components, and decorative items. The mechanism of liquid metal embrittlement to copper and copper alloys includes: mercury penetrates along grain boundaries, causing intergranular fractures. Primary materials. Number 4 is nickel and nickel-based alloys. Its susceptibility includes certain nickel alloys, especially those with high purity or specific microstructural features, can be susceptible to mercury or cadmium LME. Application of nickel and nickel-based alloys mostly on nuclear reactors, chemical processing equipment, The mechanism of liquid metal embrittlement to nickel and nickel-based alloys includes, similar to steels, infiltration along grain boundaries weakens. The structure. Primary materials number 5 is titanium and titanium alloys. Its susceptibility includes, less commonly affected but can occur in environments with mercury or other liquid metals, application of titanium and titanium alloys mostly on marine environments and aerospace components. Here's the additional factors influencing material susceptibility. The first is microstructure factors, includes, fine-grained materials tend to be more susceptible because grain boundaries provide pathways for infiltration, presence of microstructural flaws, inclusions, or residual stresses increases risk. The second is material purity, includes, high-purity materials with fewer grain boundary precipitates are more vulnerable, alloying elements can influence wettability and infiltration. The third is stress state, includes, applied tensile stresses or residual stresses can promote crack initiation and propagation in susceptible materials. The additional materials and situations, includes, Inconel and other high-performance alloys may also be vulnerable if exposed to certain liquid metals under specific conditions. Composite or coated materials may be protected or vulnerable depending on the coating's integrity and the environment. In essence, the primary materials susceptible to LME are ductile metals and alloys that have microstructures with abundant grain boundaries, are in contact with specific liquid metals like mercury, zinc, cadmium, lead, bismuth, or tin, experience tensile stresses, residual stresses, or environmental conditions favoring infiltration. Understanding the susceptibility of these materials is vital for designing systems to prevent LME damage, such as avoiding exposure to liquid metals, applying protective coatings, or selecting alternative materials. Liquid metal embrittlement or LME damage mechanisms. Critical factors based on API 571, number A, LME occurs in very specific combinations of metals in contact with low melting point metals such as zinc, mercury, cadmium, lead, copper and tin. Typical combinations of industrial significance are shown in Table 4, 9, 300 series SS susceptible to LME when combined with zinc as molten metal, copper alloys susceptible to LME when combined with mercury as molten metal, alloy 400 susceptible to LME when combined with mercury as molten metal. Aluminum alloys susceptible to LME when combined with mercury as molten metal, high-strength steel susceptible to LME when combined with cadmium and/or lead as molten metal. Number B, high tensile stress promotes cracking. However, cracking can initiate simply through contacting the molten metal with the susceptible alloy. Very small quantities of the low melting point metal are sufficient to cause LME. Number C, tensile stress contributes to crack propagation rates. Cracking under load can be extremely rapid such that cracks may pass through the wall within seconds of contact with the molten metal. Number D, cracking can occur after long periods of time when contaminated surfaces are exposed to liquid metals. Number E, a susceptible metal in contact with a low melting metal at low temperatures may crack later when the temperature rises above the melting temperature of the low melting alloy. Here's a detailed explanation of the critical factors influencing liquid metal embrittlement. LME, damage. Liquid metal embrittlement, LME, is a complex phenomenon that depends on several interrelated factors. These factors determine whether LME will occur, how severe it might be, and how quickly damage progresses. Understanding these factors is essential for predicting, preventing, and managing LME in engineering applications. Critical factors of liquid metal embrittlement or LME damage. Number 1, material susceptibility, includes, number A, microstructure and grain boundaries. Grain boundary characteristics. High-angle grain boundaries are more susceptible due to increased energy and pathways for liquid metal infiltration. Fine-grained microstructures provide more grain boundary area, increasing vulnerability. Microstructural defects, inclusions, microvoids, or residual stresses at grain boundaries facilitate crack initiation. Microstructural heterogeneities can act as sites for liquid metal segregation. Number B of material susceptibility is material composition and purity. Alloy composition includes, certain alloying elements can either inhibit or promote wetting and infiltration. For example, high-purity metals may be more susceptible due to fewer impurities blocking infiltration pathways. Residual and internal stresses. Stresses from manufacturing processes, welding, casting, machining, can predispose materials to crack initiation. Number B of material susceptibility is mechanical properties, includes ductility and toughness. Less ductile, high-strength materials are more prone to brittle fracture once embrittled. Hardness and strength. Higher strength can localize stresses at microstructural flaws, aiding crack nucleation. Critical factors of liquid metal embrittlement or LME damage. Number 2 to be considered is type and properties of the liquid metal. Number A, wetting behavior. Wettability, the ability of the liquid metal to spread over and adhere to the solid metal surface is crucial. Good wettability ensures infiltration along grain boundaries. Surface tension, lower surface tension promotes wetting and penetration. Type and properties of the liquid metal. Number B is chemical compatibility, segregation tendency. The liquid metal's chemical affinity for the solid influences infiltration. For example, mercury readily wets aluminum and steels, making them more vulnerable. Type and properties of the liquid metal. Number C is melting point and viscosity, temperature dependence. Elevated temperatures improve wetting but also increase diffusion rates. Liquid metals with low melting points or that are liquid at operating temperatures can infiltrate more easily. Critical factors of liquid metal embrittlement or LME damage. Number 3 to be considered is environmental and operating conditions, includes, number A, temperature. High temperatures enhance wetting and infiltration but can also accelerate diffusion of liquid metal into grain boundaries. Temperature gradients, differential thermal expansion can induce stresses, promoting crack initiation. Environmental and operating conditions factors. Number B, mechanical stress, applied tensile stress, essential for crack propagation. Stress helps open grain boundaries for infiltration. Residual stress, stresses remaining from manufacturing or fabrication processes can predispose to LME. Environmental and operating conditions factors. Number C, stress state, tensile versus compressive. Tensile stresses favor crack initiation and growth. Compressive stresses generally inhibit crack propagation. Number D, exposure duration. Longer exposure to liquid metal increases infiltration depth, weakening the microstructure and increasing fracture risk. Critical factors of liquid metal embrittlement or LME damage. Number 4 to be considered is microstructural and external factors, includes, number A, surface condition, surface roughness, oxidation, or coatings can influence wettability and infiltration. Corroded or oxidized surfaces may either hinder or promote infiltration depending on the chemistry. Microstructural and external factors. Number B, presence of microstructural flaws, microcracks, voids, or inclusions act as initiation sites where liquid metal can penetrate. Microstructural and external factors. Number C, alloying elements and impurities. Certain impurities can either block or facilitate infiltration. For example, oxide layers may act as barriers or pathways for infiltration depending on their nature. Critical factors of liquid metal embrittlement or LME damage. Number 5 to be considered is kinetic factors, includes, number A, rate of infiltration, influenced by temperature, wetting behavior, and microstructure. Faster infiltration leads to quicker embrittlement and failure. Number B, diffusion of liquid metal. The rate at which liquid metal diffuses along grain boundaries impacts the severity and progression of LME. The critical factors influencing LME damage are interdependent. The likelihood and severity of embrittlement depend on the combined effects of material susceptibility, the properties of the liquid metal, environmental conditions, and mechanical stresses. Altering or controlling these factors, such as material selection, environment, stress management, and surface treatments, can effectively mitigate the risk of LME-induced failures. Liquid metal embrittlement damage affected units or equipment based on API 571, number A, during a fire, molten metals may drip onto or contact a susceptible metal. Examples include melted zinc galvanizing, cadmium electrical housings, tin or lead from solders, and melted copper components. Number B, LME can occur in any location where the LME couples are found. A common example is 300 series SS piping or vessels in contact with, or previously rubbed against, galvanized steel. See Figure 4-157 sketch of a stainless steel elbow that suffered liquid metal embrittlement as a result of dripping molten zinc during a fire. See Figure 4-158, photomicrograph of a section of the elbow in Figure 4-157, illustrating the intergranular nature of zinc-filled cracks in stainless steel. Number C. In refineries, mercury is found in some crude oils and can condense in the atmospheric tower overhead system, thereby embrittling brass, alloy 400, titanium or aluminum exchanger components. Number D. Failure of process instruments that utilize mercury can introduce the liquid metal into refinery streams. See Figure 4-159, liquid metal embrittlement of Monel caused by mercury in an FCC gas plant overhead drum. Number E. LME of aluminum components has occurred in LNG facilities and cryogenic gas plant components due to condensation of liquid mercury. Here's a detailed explanation of the units or equipment affected by liquid metal embrittlement, LME, damage. LME can compromise a wide range of industrial units and equipment, especially those involving the contact of susceptible materials with liquid metals under stress. The specific equipment affected depends on the operational environment, materials used, and exposure conditions. Affected units and equipment in liquid metal embrittlement, LME, damage, includes, number 1, nuclear reactor components, includes, number A, fuel cladding and structural materials such as metal tubes, plates, or structural elements that contain or support nuclear fuel. Materials uses commonly stainless steels, zirconium alloys, or other high-strength alloys. Fuel cladding and structural susceptibility for this materials would be mercury or other liquid metals introduced during certain reactor operations or accidents can infiltrate grain boundaries, leading to embrittlement. The impact of fuel cladding and structural materials are potential for crack initiation, propagation, and failure of containment or structural integrity. Number B. Reactor coolant systems such as pipelines, heat exchangers, and valves. Materials uses commonly steel alloys, nickel-based alloys. Reactor coolant system susceptibility for this materials would be exposure to liquid metals like mercury or lead bismuth eutectic in advanced reactor designs or experimental setups. The impact of reactor coolant systems are corrosion, cracking, and leaks. Affected units and equipment in liquid metal embrittlement, LME, damage. Number 2, chemical and processing equipment, includes, number A, heat exchangers and condensers. Components with metal surfaces in contact with liquid metals such as mercury or zinc, heat exchangers and condensers. Susceptibility in chemical processing involving liquid metal catalysts or coolants. Impact of LME to heat exchangers and condensers is to reduced mechanical strength, leading to leaks or catastrophic failure. Chemical and processing equipment. Number B, reactors and reactors internals. Reactors where liquid metals serve as coolants or process media. Examples: fast breeder reactors using liquid sodium, systems with mercury or lead. Impact: embrittlement of internal structures causing deformation or rupture. Affected units and equipment in liquid metal embrittlement, LME, damage. Number 3, aerospace and marine equipment, includes, number A, marine propulsion systems. Components exposed to mercury or other liquid metals in certain marine applications. Susceptibility: mercury used historically in some marine instrumentation. Impact: structural failure due to embrittlement. Aerospace and marine equipment. Number B, aerospace components. High-performance alloys exposed to liquid metal environments during manufacturing or operation. Impact: microcracking and potential failure under operational stresses. Affected units and equipment in liquid metal embrittlement, damage. Number 4, electronics and instrumentation, includes, number A, electronic connectors and switches. Components where mercury is used in switches or thermometers. Susceptibility: mercury infiltration can cause embrittlement of contact points. Impact: malfunction or failure of electrical components. Electronics and instrumentation. Number B, sensors and measuring devices. Devices with metal contacts exposed to mercury or other liquid metals. Impact: loss of integrity and accuracy due to embrittlement. Affected units and equipment in liquid metal embrittlement, damage. Number 5, manufacturing and fabrication units, includes, number A, welding and assembly equipment. Equipment used to assemble or repair components made of susceptible metals. Susceptibility: exposure to liquid metals during cleaning or manufacturing processes. Impact: microstructural weakening, leading to premature failure. Manufacturing and fabrication units. Number B, coating and surface treatment units. Systems applying coatings to protect against corrosion, impact, interaction with liquid metals can induce embrittlement in coated materials. Affected units and equipment in liquid metal embrittlement damage. Number 6, special environments and experimental facilities, includes, number A, laboratories handling liquid metals. Facilities working with mercury, lead, bismuth, or zinc, susceptibility, equipment, containment vessels, and transfer lines, impact, structural degradation, leaks, or accidents, special environments and experimental facilities. Number B, material testing and research units. Testing rigs designed to study material behavior in liquid metal environments, impact, equipment itself may experience embrittlement, affecting experimental results. Liquid metal embrittlement. Final notes, the severity and extent of damage depend on factors such as exposure duration, temperature, applied stresses, and material microstructure. Proper material selection, protective coatings, and design considerations are critical to prevent LME damage in susceptible units. Regular inspection and monitoring are essential for early detection of embrittlement-related issues, especially in critical infrastructure like nuclear reactors. Liquid metal embrittlement. Appearance or morphology of damage based on API 571. Number A, damage resulting from LME will appear as brittle cracks in an otherwise ductile material. LME can only be confirmed through metallography by the presence of intergranular cracks, usually filled with the low-melting metal. Number B, techniques such as spectrographic analysis may be required to confirm the presence of the molten metal species. Here's a detailed explanation of the appearance or morphology of liquid metal embrittlement, LME, damage. LME manifests as characteristic microstructural features and macroscopic surface indications that reflect the underlying brittle fracture process induced by liquid metal infiltration. Understanding these morphological features is essential for diagnosing LME-related failures and distinguishing them from other types of damage. Appearance and morphology of liquid metal embrittlement, LME, damage, includes, number 1, macroscopic features, includes, number A, brittle fracture surfaces. The appearance of brittle fracture surfaces are flat, shiny, and granular surfaces typical of brittle fracture, often lack the ductile features such as ductile dimples characteristic of ductile failure. The fracture surface may be intergranular, along grain boundaries, or transgranular, through grains, depending on the mode of embrittlement. The color and texture of brittle fracture surfaces are, usually, metallic luster with a smooth or slightly granular texture, may show mirror-like regions indicating rapid crack propagation. The size and shape of brittle fracture surfaces are, fracture features can range from microscopic to visible with the naked eye, often appearing as clean, ragged, or faceted surfaces. Number B of macroscopic features is surface cracks and flaws. The appearance of surface cracks and flaws are, cracks may originate at surface defects, microvoids, or inclusions. In some cases, intergranular cracks run along grain boundaries, giving a network-like appearance. The pattern of surface cracks and flaws are, often interconnected, forming a network of microcracks or macrocracks. Cracks may be parallel to the surface or perpendicular, depending on stress and infiltration pathways. Number C of macroscopic features is evidence of liquid metal penetration. The evidence is discoloration or deposits. Residual liquid metal or corrosion products may leave deposits or discoloration, especially if the infiltrating metal is reactive, such as mercury, lead. The evidence in corrosion layers is sometimes a corrosion film or oxide layer forms at the crack tips or along grain boundaries, indicating infiltration. The appearance and morphology of liquid metal embrittlement, LME, damage. Number 2 is microstructural features, includes, number A, grain boundary embrittlement, includes, intergranular fracture mode, cracks propagate along grain boundaries, which appear widened or decohesioned. Grain boundaries may show voids or microcracks at the interface. The features of grain boundary embrittlement are, intergranular corrosion or attack zones are often evident under microscopy. Grain boundaries may be decorated with residual liquid metal or corrosion products. Microstructural features. Number B, microvoids and microcracks. The appearance of microvoids are small, spherical cavities within the grains or along boundaries. The appearance of microcracks are often intergranular or transgranular. Distribution of microvoids and microcracks includes, concentrated near the surface or at grain boundary triple points. may coalesce to form larger cracks. Microstructural features number C, infiltration pathways, liquid metal penetration channels, evidence of liquid metal infiltrating along grain boundaries, microvoids, or defects. These pathways may appear as dark lines or areas under. Microstructural features number D, fracture surface morphology. The features of fracture surface morphology includes, characterized by cleavage planes and step-like features typical of brittle fracture, may show dimpled regions if partial ductility exists, but predominantly brittle features dominate. Fracture mode of fracture surface morphology includes, intergranular fracture dominates in embrittled regions. Transgranular brittle fracture may also occur, often with faceted features. Number 3 of appearance and morphology of liquid metal embrittlement damage is specific morphological indicators of LME. For feature is intergranular cracking that described as, cracks follow grain boundaries, and the significance indicators is signature of embrittlement along grain boundaries via liquid metal infiltration. For feature is smooth, mirror-like fracture surfaces that described as, rapid, brittle crack propagation, and the significance indicators is indicates brittle failure. Mode typical of LME. For feature is microvoids and microcracks that described as, tiny cavities and cracks within grains or boundaries, and the significance indicators is initiation sites for fracture. For feature is residual liquid metal deposits that described as, presence of metallic or corrosion deposits at cracks, and the significance indicators is evidence of infiltration and embrittlement process. For feature is widened grain boundaries that described as, boundaries appear decohesioned or widened, and the significance indicators is result of liquid metal weakening the boundary strength. Number 4 of appearance and morphology of liquid metal embrittlement damage is visual and microscopic examination, includes, number A, optical microscopy, reveals surface features such as cracks, grain boundary decohesion, and fracture morphology. Number B, scanning electron microscopy or SEM, this SEM provides high-resolution images showing, grain boundary attack, microvoids and crack propagation paths, residual liquid metal deposits. Visual and microscopic examination number C, energy dispersive X-ray spectroscopy or EDS, confirms presence of infiltrating liquid metal or corrosion products along cracks or at grain boundaries. The morphology of LME damage distinctly reflects brittle fracture mechanisms facilitated by liquid metal infiltration. Recognizing these features through visual inspection and microscopic analysis is critical for diagnosing LME in failed components and understanding the failure mechanisms. Liquid metal embrittlement or LME damage prevention and mitigation based on API 571, number A, LME can only be prevented by protecting metal substrates from coming into contact with the low melting metal. For example, galvanized steel components should not be welded to 300 series SS. 300 series SS should be protected to avoid contact with galvanized components and overspray from zinc and inorganic zinc coatings. Number B, once cracking from LME has initiated, grinding out the affected area is not an acceptable fix. Here's a comprehensive, detailed explanation of prevention and mitigation strategies for liquid metal embrittlement or LME damage. LME is a critical failure mode in materials exposed to certain liquid metals, often leading to catastrophic brittle fracture. Preventing or mitigating LME involves a combination of material selection, design considerations, operational controls, and maintenance practices. Prevention and mitigation of liquid metal embrittlement or LME damage includes, number 1 is material selection and alloy design, includes, number A, use of resistant materials, avoid susceptible alloys, materials such as certain stainless steels, nickel-based alloys, and zirconium alloys are prone to LME with specific liquid metals like mercury or lead. Select alternative materials. Use aluminum alloys, titanium, or ceramics where compatible, or those with high resistance to liquid metal. Infiltration. Number B of the material selection and alloy design is microstructure control, includes, grain size optimization, fine-grained microstructures enhance toughness and reduce susceptibility, impurity reduction, minimize impurities and inclusions that can act as crack initiation sites, heat treatment. Proper heat treatments can improve grain boundary strength and reduce embrittlement susceptibility. Number C of the material selection and alloy design is coatings and surface treatments, includes, protective coatings, apply corrosion-resistant or impermeable coatings, e.g., ceramic, nickel plating, to prevent liquid metal contact, barrier layers, use diffusion barriers to inhibit liquid metal infiltration along grain boundaries. Prevention and mitigation of liquid metal embrittlement or LME damage. Number 2 is design considerations, includes, number A, minimize stress concentrations, design for low residual stresses, reduce welding residual stresses, machining marks, and geometric stress risers, component geometry, avoid sharp corners, notches, or abrupt thickness changes that concentrate stress. Design considerations. Number B is control of operating environment, includes, limit liquid metal exposure, design systems to prevent liquid metal leaks or spills, temperature management, operate below the threshold temperature where LME is most active, if possible, flow control, ensure smooth, laminar flow of liquid metals to reduce turbulence and localize stresses. Design considerations. Number C is structural redundancy. Incorporate safety margins and redundant load paths to prevent catastrophic failure if embrittlement occurs. Prevention and mitigation of liquid metal embrittlement or LME damage. Number 3 is operational and process controls, includes, number A, leak prevention and detection, regular inspection, use non-destructive testing, NDT, techniques such as ultrasonic, radiography, or dye-penetrant testing to detect early cracks or leaks, leak tightness, maintain high standards of sealing and joint integrity. Operational and process controls. Number B is environmental control, includes, temperature regulation, maintain operational temperatures within safe limits, chemical control, use additives or corrosion inhibitors to reduce aggressive interactions with liquid metals. Operational and process controls. Number C is stress management, includes, reduce operational stresses, limit mechanical loads, vibrations, and thermal stresses during operation, stress relief procedures, post-welding or manufacturing heat treatments to reduce residual stresses. Prevention and mitigation of liquid metal embrittlement or LME damage. Number 4 is maintenance and inspection, includes, number A, routine inspection, perform regular visual, ultrasonic, or other NDT methods to detect early signs of embrittlement or cracking, use acoustic emission monitoring for real-time detection of crack growth. Maintenance and inspection. Number B is material replacement, includes, replace components showing signs of embrittlement or micro-cracking before failure occurs, implement a preventive replacement schedule based on service life and inspection results. Maintenance and inspection. Number C is cleaning and surface preparation, includes, remove residual liquid metal deposits or corrosion products that can accelerate embrittlement, use compatible cleaning agents that do not damage protective coatings. Prevention and mitigation of liquid metal embrittlement or LME damage. Number 5 is protective coatings and barriers, apply corrosion-resistant coatings, such as nickel, ceramic, or polymer coatings, to prevent direct contact between the liquid metal and susceptible substrate, barrier layers. Use diffusion barriers such as aluminum or ceramic layers to prevent liquid metal penetration along grain boundaries. Prevention and mitigation of liquid metal embrittlement or LME damage. Number 6 is specialized treatments and innovations, includes, number A, alloying additions. Incorporate elements that form stable, protective oxide layers or reduce liquid metal affinity, specialized treatments and innovations. Number B is grain boundary engineering. Techniques such as thermomechanical processing to produce special grain boundary character distributions that are less susceptible to infiltration. Specialized treatments and innovations. Number C is use of sacrificial layers. Employ materials that preferentially absorb or react with the liquid metal, protecting the main structural material. Preventing and mitigating LME require an integrated approach combining materials science, mechanical design, operational controls, and maintenance practices. Early identification of susceptible conditions, careful material and system design, and rigorous inspection regimes are vital to prevent catastrophic failures associated with LME. Liquid metal embrittlement or LME damage inspection and monitoring based on API 571, number A, cracks can be detected with MT examination for ferritic steel and PT examination for 300 series SS and nickel base alloys, number B, because of the high density of mercury, radiography has been used to locate deposits inside heat exchanger tubes. Here's a detailed overview of inspection and monitoring methods used to detect liquid metal embrittlement or LME damage, including their principles, applications, advantages, and limitations. LME is characterized by micro and macro scale features such as intergranular cracks, microvoids, and surface flaws. Detecting these features early requires a combination of nondestructive testing, NDT, techniques and monitoring strategies tailored to identify subtle signs of embrittlement and crack growth. Inspection and monitoring methods for detecting liquid metal embrittlement, LME, damage. Number 1 is visual inspection. Its principle is direct visual examination of surface conditions using magnification tools. Application visual inspection is to detect surface cracks, corrosion products, discoloration, and surface flaws. Visual inspection suitable for accessible regions and in situ inspections. Visual inspection techniques includes visual with naked eye, magnifying glasses or portable microscopes, remote video inspection systems. Visual inspection advantages includes quick, inexpensive, straightforward, good for identifying gross surface damage. Visual inspection limitations includes visual inspection cannot detect subsurface or microcracks. It depends on accessibility and operator skill. Inspection and monitoring methods. Number 2 is dye penetrant testing or DPT. Its principle is surface breaking cracks or flaws are revealed by applying a liquid dye penetrant that seeps into cracks. After excess removal, a developer makes the dye visible. Application dye penetrant testing is to identify surface microcracks, especially intergranular cracks along grain boundaries, suitable for materials with smooth, clean surfaces. Dye penetrant testing advantages includes sensitive to small surface cracks, relatively simple and inexpensive. Dye penetrant testing limitations includes only detects surface flaws, cannot reveal subsurface or internal cracks, surface must be clean and dry. Inspection and monitoring methods. Number 3 is ultrasonic testing or UT. Its principle is surface breaking cracks or flaws are revealed by applying a liquid dye penetrant that seeps into cracks. After excess removal, a developer makes the dye visible. Application ultrasonic testing is to detect internal cracks, especially intergranular microcracks, suitable for thick or complex geometries. Ultrasonic testing techniques includes pulse echo method and phased array ultrasonics. Ultrasonic testing advantages includes detects internal flaws, quantitative assessment of flaw size and location. Ultrasonic testing limitations includes requires skilled operators, surface roughness and geometry can affect accuracy, microcracks below certain size thresholds may be missed. Inspection and monitoring methods. Number 4 is radiographic testing or RT. Its principle is X-rays or gamma rays penetrate the component, flaws appear as areas of different density or absorption. Application radiographic testing is to detect internal cracks, voids, or infiltration pathways. Radiographic testing advantages includes provides a permanent record of internal features, good for complex geometries. Radiographic testing limitations includes limited sensitivity for very small cracks, safety concerns and equipment costs, less effective for detecting microcracks unless highly sensitive methods are used. Inspection and monitoring methods. Number 5 is scanning electron microscopy or SEM. Its principle is high-resolution imaging of fracture surfaces or microstructural features. Application scanning electron microscopy is to examine fracture surfaces for characteristic LME features such as intergranular fracture, microvoids, or liquid metal residues. Microanalysis with EDS, energy dispersive X-ray spectroscopy, to identify penetrated metals. Scanning electron microscopy advantages includes provides detailed morphological and chemical information, identifies embrittlement signatures at microscale. Scanning electron microscopy limitations includes requires sample preparation, not suitable for in-service inspection, used mainly for failure analysis. Inspection and monitoring methods. Number 6 is acoustic emission monitoring. Its principle is detects transient elastic waves generated by crack initiation and growth during service. Application acoustic emission monitoring is real-time monitoring of active crack growth. It is useful for early detection of embrittlement-induced cracking under operational conditions. Acoustic emission monitoring advantages includes continuous, in situ monitoring, can detect active crack propagation. Acoustic emission monitoring limitations includes sensitive to background noise, requires specialized equipment and data analysis. Inspection and monitoring methods. Number 7 is leaks and corrosion monitoring. Its principle is detect leaks or corrosion products associated with embrittlement damage. Application. Leaks and corrosion monitoring is use of sensors, chemical analysis, or visual checks around potential leak points. Leaks and corrosion monitoring advantages includes early indication of damage progression. Leaks and corrosion monitoring limitations includes not directly identifying cracks, but indicative of damage. Inspection and monitoring methods. Number 8 is advanced and emerging techniques, includes techniques. Number 1 is phased array ultrasonics, improved flaw imaging and detection sensitivity. Techniques. Number 2 is digital radiography and computed tomography or CT, high-resolution 3D imaging of internal damage. Techniques. Number 3 is magnetic particle inspection or MPI, for ferromagnetic materials to detect surface and near-surface cracks. And techniques. Number 4 is infrared thermography, detects temperature anomalies due to crack-related heat flow. Monitoring strategies for liquid metal embrittlement includes, number 1 is regular scheduled inspections, routine visual, dye penetrant, and ultrasonic testing. Focused on high-risk areas such as welds, joints, and surfaces prone to liquid metal contact. Monitoring strategies. Number 2 is in-service monitoring, acoustic emission sensors to detect crack initiation and growth during operation. Leak detection systems to identify early signs of containment failure. Monitoring strategies. Number 3 is corrosion and leak sensors, use of chemical sensors, pressure monitoring, or flow sensors to detect leaks of liquid metal. Monitoring strategies. Number 4 is structural health monitoring, integration of sensors and data acquisition systems for real-time damage assessment. Effective detection of LME damage involves a combination of methods tailored to the specific application, material, and stage of damage. Routine inspections, coupled with real-time monitoring during operation, significantly enhance the ability to detect early signs of embrittlement and prevent catastrophic failures. Thank you.